Hello, today we're going to talk about calorimetry and phase changes, lecture 31. We're going to talk about 6.4 heat capacity and calorimetry, 6.5 energy of phase changes. The learning objective is to calculate the heat Q absorbed or released by a system undergoing heating and cooling based on the amount of substances, the heat capacity, and the change in temperature. We're also going to explain the changes in heat absorbed or released by a system undergoing a phase transition. And we'll be talking about moles and the molar enthalpy of phase transition. A heating curve is defined as a way to describe how energy changes when matter undergoes phase changes. So if I go from a solid to a liquid, we'll be using what we call a delta H of fusion. Vaporization is going to go from a liquid to a gas, and that is defined as delta H VAP. So a heating curve shows that relationship by adding heat and the temperature of a substance as we go from left to right. These are parts of the heating curve where an increase in added heat energy leads to an increase in temperature and therefore an increase in kinetic energy. So a gas will have more kinetic energy than a solid, while liquid will have a middle kinetic energy. And we're going to calculate the amount of heat energy added as Q equals mc delta T. So in this example right here, we're going to find that M stands for mass, C stands for heat capacity, specific heat capacity, and delta T stands for change. And these are parts of the heating curve that adding heat does not increase in kinetic energy. In other words, the temperature does not go up. Instead, the energy is being put into the system to increase the potential energy of the system, which in turn will allow it to undergo what we call a phase change. And we're going to calculate that heat energy as Q equals N delta H. So that's going to be the phase where we talk about melting and vaporization. So let's talk about what happens when you add heat energy to temperature and to kinetic energy. So heat capacity is when a system has absorbed heat, Q, and the temperature has changed by delta T. And we talk about how experiments show this, how they're proportional to temperature. So as temperature rises, we have an increase in energy or heat, and that's determined by Q. And that proportionality constant is defined as heat capacity, or C. So I want you to make sure you explain and understand that idea that Q is equal to C times delta T. So in this example right here, we know that the change in temperature is proportional to whatever the C value is multiplied by delta T. And the heat capacity of a system is defined as a quantity of heat required to change its temperature by 1 degree Celsius. And the heat capacity can be reported as molar heat capacity or specific heat capacity. Which do not depend on the amount of matter being heated. So we're going to talk about how this is going to work in a bit. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degrees, and it has a units of joules over mole times C. So let's talk about specific heat capacity. Specific heat capacity of a material is the amount of heat required to change the temperature of 1 gram of a substance by 1 degrees, and its units is joules over GC. As an example, if I ask you which one takes longer to heat, water or sand, generally, water takes a longer time because water has a higher heat capacity. So the specific heat capacity of water is 4.18 joules per gram per Celsius, which means it takes 4.18 joules of heat to raise the temperature of 1 gram by 1 degrees. While for sand, it's 0.742 joules per gram, which means it takes 0.742 joules to raise the temperature of the sand by 1 degree. So the question here is, why would the sand have a lower heat capacity? And it has to do with its bonds and the way the chemical structure. But generally, a lower heat capacity means it's easier to heat up. So the question is, which one heats up faster? And the answer here would be sand because it has a lower heat capacity. So let's talk about calculation. So when we calculate how much heat must be absorbed, we must use the equation of Q equals MCAT. Now, Q equals MCAT refers to the equation of how much heat is going to be released. Where Q stands for joules, or how much heat is absorbed or released. It could be negative or positive. M stands for mass, and C stands for specific heat capacity, or joules over GC. While delta T refers to the final temperature or initial, and it doesn't really matter. It could be Celsius or Kelvin because we're talking about differences. In the thermochemistry for the AP exam, you're going to have your QMCAT formula at the top, along with your QMC and delta and C here, so you can always refer to this table. Now let's talk about heat capacities means different temperature changes. So let's talk about the difference between aluminum and lead. In aluminum, the heat capacity is 0.900 joules per GC, while the heat capacity of lead is 0.130. Adding 1,000 of energy to 100 grams of your substance results in different temperature changes. So let's go ahead and compare two formulas. For aluminum, it's going to be Q is equal to M over C. And if you go back and plug everything in, you're going to get 1,000 joules divided by 100 times 0.9. So the difference here is going to be that 0.9 compared to something like lead. And our answer here would have a difference of 11.1 degrees Celsius. Now let's talk about lead real quick. Lead's going to be the exact same thing. The difference is we're going to use 0.130 instead of 0.9, and we expect that there will be a larger temperature change. So the answer here is the lower the heat capacity, the larger that change. So small substance with a small heat capacity will heat up much more quickly and easily than a material with a high heat capacity because it takes less energy to change its temperature. So metals generally have very low heat capacities. So let's take a look at calculations with temperature changes and heat capacity. So here it reads a 27.00 gram of an unknown metal was heated until 420 joules of heat had been added. The graph to the right shows the data, kind of like they're doing an experiment. So a couple of things here that you see is that over time the temperature generally should increase, but sometimes you'll see a graph where the temperature stays flat. And the question is, determine the temperature change of the metal. So go ahead and pause the video and go ahead and start it in, and we're going to continue this in class.